All right, you guys have any questions? Concerns? Suggestions? Observations? How important is it? In the grand scheme of things, relative to your life, probably not very much. But in terms of, I did ask you homework questions. You'll get a clue from the homework how deep into it I expect, and that'll be the similarity on the test. What we discuss in here is the depth I figure you'd get. The chapter does go into greater depth than I am, and there's more formulas and calculations. I don't intend to make you calculate the things. I want you to understand the concepts. We'll review some of the key points, and I'll do more today. And then we get to review Friday, everything. So if you're still confused, let me know by then. But I don't expect that. It took me multiple times. It takes physicists. Any physicist that says they understand relativity and quantum mechanics completely, they're fooling themselves. It's still confusing. But there's some major points and consistencies that you can get, and I expect you to. Was that too vague? I'm going to start with some clicker questions that ask about some of the stuff we discussed last time. And those are some of the main points I hope you get. So if you miss every one of these, you got more work to do. And then I'll ask you some more either at the end of this one or the beginning of next time for what we covered today. So. Yeah, because since I didn't get it the first time, I don't expect you guys to get it the first time. But realize Chapter 35 isn't something where you can just breeze through it and go, oh yeah. You're going to have to think about that stuff and reread. It doesn't come naturally to most folks. Anything else? Welcome, welcome. All right, well, let's ask those questions then. Clicker time. All right, there's the session ID, channel number, and the first question, polling open. We'll see how it goes. Michelson-Morley. It's in your text. We discussed it. That was the light splitting up, going two different ways, coming back together to make some interference pattern. They were trying to show one thing, but the result of the experiment showed something else. What did it show? The experiment actually showed what? Taught us in the world something we didn't think was the way it was. I don't think I've ever used this for my daughter. It's one of those teaching moments where if an experiment fails, it's okay, we learned more from our failures, blah, blah. And I've never brought this up. But well, you see, dear, Michelson and Morley, they attempted to show something. They were dead set. They believed it was going to work and show it and put everything to rest. And it failed. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and okay, you guys are split between A and B. Good, at least that's the right half. It's one of those. The speed of light is not relative or the speed of light is relative. The experiment showed that either the speed of light is not relative to anything else, it's absolute, or the speed of light is relative depending on what you are comparing it to. Given that in mind, discuss with your neighbor and vote again. Because you guys are mostly split. Either remember what you read in the chapter or we discussed last time about light and its relative motion. Since I don't hear you talking, what do you think?
I have no neighbors. I'm all alone over here.
Which one did you vote? Which one did you put?
Oh, I voted.
You voted A? You feel strongly about that? What'd you vote? Tell him why. See if he agrees. Yeah, if you've convinced your neighbor or changed, well, yeah, revote if you've, whatever decision you've made this time, revote.
And so I think a lot of people thought that it might have been relative.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Meh. Oh, looks like most of you have convinced the others to be A. Good. You're right. They were trying to show that light was relative to motion. Remember, the Earth's moving one way, so if the light's going that way, maybe they'll get a faster result versus the light that went perpendicular to the direction of the Earth. That shouldn't be affected by the speed of the Earth. And they expected to see a difference, showing that light is relative to something else. They never saw a difference, and it was sensitive enough to do so, thus counter-proving that light is not relative to anything else. It's the speed of light, c, is a constant for any direction. And that's one of our postulates that the special theory of relativity is based on. It's an assumption, and given that, a lot of these results come out. That I expect you to know. All right, go. Einstein stated that the laws of physics are... Are they the same, or do they change? What's it depend on, or does it? Your clue is this is the second postulate or assumption that the special theory of relativity is based on. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Meh. Okay, we got a majority being D. You are correct. It looked like the next largest was C. So let's differentiate again between the laws of physics are the same. Good. Most of you got that. But for all frames of reference, or just uniformly moving frames of reference? And it's D, meaning frames of reference where the speed is constant. You're not changing your motion, and accelerating and decelerating, and adjusting your velocity. Those frames where you're accelerating are inertial reference frames. Because if you try to accelerate something or change its motion, you can feel that fighting you, that resistance. Inertial frame of reference. Another term that your book doesn't use as much, but I've been saying, a uniformly moving frame of reference, D, is a non-inertial frame of reference. Same thing. This makes more sense, a uniformly moving.
So, according to that last question or that last experiment, if we're moving against or in opposite directions to something that's moving at the speed of light, it's not like we'll see the net effect of the two movements. It's always, like we'll always observe 3 to 10 to the power 8 meters per second or something?
That's correct. That's correct. So if you're on a... Hey, I think that was one of my questions, actually. Well, I'll give it to you. Correct. No matter who's measuring the speed of light, whether they're in a uniformly moving frame of reference or not, or which direction they're moving, they're all going to measure the speed of light to be the exact same value. It doesn't seem to add or subtract onto their frame of reference motion, which was weird back then. It's a little more settled among scientists, but I don't know what you guys think.
But the perceived speed will be different if we're in a moving...
No. The perceived speed of light?
Yeah.
No, the speed of light's constant. And the same for everybody in any uniformly moving frame of reference. Someone doesn't perceive it as being faster or slower, the speed of light. If they go to measure it, they're going to get the exact same value as you'll get, and you'll get, and you'll get, if you're all in uniformly moving reference frames, or not moving, because that's uniform motion of zero.
Doesn't that go against the light contraction thing?
No, it does not. Tell me what you're thinking. It doesn't go against length contraction.
Well,
Oh, give it a shot.
say light's always constant, but I can't remember what it's called.
The Lorentz factor?
Like if something's flying past you, it looks smaller.
Yes, we're covering that today.
I don't know, because light is sort of vision, it would seem like they go against
Yeah, it's that what you're getting at is that they seem to contradict for length contraction of this. Space. People won't agree on that anymore. Remember our simultaneous experiment? Where something simultaneous in my reference frame might not necessarily be simultaneous in yours, if it's a uniformly moving reference frame. We can see events occurring at different times. What gets changed then is space seems to be different for you versus me. Length, positions. So we can disagree on that. But we will also disagree on time. The time it took for the light to get to you from the two sides or my side, or when the event occurs. But the ratio between space and time, you guys have heard of the space-time continuum? Star Trek fans. That relationship, the ratio of space over time is the constant. That's the unifying factor. And space over time, position over time is a speed of light. Space over time, speed of light, that's the constant. So, and it actually came about the other way. Because light is a constant, these things can be different for folks, but the ratio still has to stay the same. So when I discuss the special theory of relativity with most folks, we always invariably seem to come up with, it seems to contradict itself. But you have to look at both sides, and that ratio always stays the same, even though we can disagree on space and time. And it's important for me to emphasize again, both are right. The moving reference frame and you at rest can disagree on space and can disagree on time, and you're both right. There's no absolute reference frame. Neither of you is the right answer, and the other one just is confused or perceives it that way. No, it's that way for them, it's that way for you. It's weird. All motion's relative. It's the kind of bottom line of special relativity. Let's see, I wanted to do this one. Well, we just answered that. So I'll give you less time. That way you can get credit for it. Go. See if you picked that up on what I just said again. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Most of you think B. That's correct. So those of you that say A, can you tell me some of your thoughts? So events that occur simultaneous in one reference frame will be seen simultaneous in the other one. Can you explain some of your reasoning behind that for me? So I can help you realize that it doesn't necessarily have to be the same. No takers. Well, a fair percentage of you voted that one. When I help you get it right on homework and test. That's all right. I don't want you to be embarrassed either, but... So if light travels a certain distance, it takes a certain time. We just discussed how distance and time can vary. Thus, two events can seem simultaneous for one reference frame and not for another.
I think what's hard for me to grasp is how abstract what we're talking. It's just so like these events or like what are these events?
Remember me doing light? We usually do with light just because these are fast things. You know, and I turn on a light bulb, it flashes. And the light waves from there, even though it's super fast, do take a certain amount of time, because the speed of light, to travel to the walls, let's say. And if I'm in the middle, that distance and that distance are the same. The velocity of light doesn't change, so it should take the same amount of time to get to both walls. So I see it hitting the walls at the same time. It's simultaneous. If you're cruising by in a spaceship really fast, then the light comes on, the waves head out, but by the time the light waves are about here, let's say, your spaceship has moved. And so the relative distance between here and there differs from here to there. I think it's more obvious if I'm in the spaceship. You guys are at rest. But the same thing will happen. Light comes on, light waves get to here. By the time the light waves are here, let's say I have shifted over to here with my light bulb, but the waves are still right here. At some point later, I'm over here, and the light waves are now maybe here. Can you see that this light wave will hit the back end of my spaceship before this light wave will hit the front end? Because the front end's kind of like running away from it. And so in that reference frame, I won't see the two events hitting the walls, the front end of my ship, as being simultaneous. But yeah, that might seem abstract. It'll work for any events. People can run a race. You can shoot a phaser at another ship. It can be when two balls land on the ground. Any two events that we're observing, if they seem to happen at the same time in one reference frame, doesn't necessarily mean it'll be the same for another reference frame moving with respect to that first reference frame, or vice versa. Yes?
What if the light waves just move the system?
Because light is an absolute speed. It doesn't change for any reference frame. It didn't seem to add or subtract with the speed of the reference frame. So maybe it's a little clearer that the result comes from that. That's why it's one of the postulates, an assumption. If it did seem to change, yeah, none of this, we wouldn't be talking. It all seemed normal.
So you see it hit that wall first, and you see it hit at the same time, right?
Yes, yeah. We would disagree. And if I move in the other way, you'd see that one happen first versus that one. So it is, motion is relative. Yeah. Correct. But no matter what. So I'm going to, in my moving spaceship, that light wave that's in my reference frame, in a sense, sees the distance from the light bulb when it flashed from here to by the time the wall comes to here. It's like it sees that space, that distance is shorter. So it takes less time to get there. That shorter distance, space, smaller time. That'll keep the ratio same for the speed of light, and vice versa on this side. It seems to have to cover more distance. We did that light clock at the end. You know, if the light goes up and down off of a mirror, it takes a certain amount of time. But if that spaceship's moving, whoosh, and you send the light wave up, it's got the speed of the rocket and the speed of light. So it's going to head off at an angle. But the ship's moving too. And then it hits the top mirror, redirected, and comes back down here. And so it travels a lot longer distance. It covers more space. To compensate, it takes longer in order to keep the speed of light the same. So the time that takes will seem to be longer for someone looking at that light wave. If I'm in the spaceship and you guys are observing it, it would look like it takes longer for you. Your measurement would be correct. But if I measure it, I'm on the spaceship with it, I'm going to get less time because I'm moving with it. It's all together. It just goes up, it goes back down.
Just kind of what we got to talk about with light.
Now this takes like 7 times to repeat the same thing, and then one of those times a light bulb will go off, no pun intended.
Just one, I've heard in other science classes I've had, does light have mass?
Does light have mass? Most scientists say no. They would say it has no rest mass. So in other words, if you could stop it, it would weigh nothing in that sense. But there's a big confusion too, even among physicists, where with mass, we like to think of mass as a lump of stuff, matter. So it's physically something. But we've also learned that mass is a measurement of inertia, how much resistance to change in motion something has. And those two things can be different, especially when you get into relativity. That's kind of what prompted general relativity. And at the very end of this chapter, we have the most famous equation ever. You guys know what it is. E equals mc squared, where E is energy, m is mass, c is the speed of light squared. And basically, Einstein showed that energy is proportional to mass. He never used the word mass. He always used inertia. So don't think of this as a lump of stuff, but more of its resistance. And so anything that has mass, inertia, has a corresponding energy value with it, and vice versa. If you got energy, we've talked about energy, potential energy, kinetic energy, heat, thermal energy, then there's a corresponding inertia associated with that. And so with light, it has energy, and so it has some inertia, but most scientists tend to say there's not a lump of something there. And they also say that if you stopped light, it would not exist, because it's never at rest. But technically, light has no rest mass, meaning if it weren't moving, there would be nothing to it. It'd have no inertia or resistance. But it's always moving. Thus, there's some energy associated with it and some inertia associated with it.
Does that E equals mc squared have any relationship to the 1/2 mv squared?
This is there's another good debate. How do you do this? Is it E? Is it the rest energy? Is it the total energy? And that depends on the context. I won't confuse you. But in my mind, I think of this as rest mass. In other words, mass is kind of like congealed energy. And so just the fact that something exists, like this book, internally there's molecular bonding and the strong and weak nuclear forces and molecular forces and electrostatic forces, and all of those stores energy. There's binding. It would take work to separate these apart, energy, to change that. So it contains its own amount of energy. If you add all those up, you can think of it as this. Now we give it motion. And well, now it has kinetic energy on top of that. So some people will differentiate and they'll say energy is kinetic energy plus this rest energy. For our purposes, I don't care if you want to think of it as total energy or not. But there's something to it. You can have the energy associated with motion, but you can also have this just innate energy because it has inertia. And that's what Einstein added on to this scene. For Einstein, when he was studying, they weren't sure what this was. They saw this factor, mc squared, and they realized it's a form of energy. Some people thought it was a new form of energy. They didn't know what to call it. Today, we generally call it the rest energy. This is good. I think I wanted to ask you one more. Yeah, that's right. This one. This was essentially your question. See if you get it right. So you're in a ship moving at the speed of light somehow, and then you shoot a drone forward at speed c relative to the ship. So the ship's moving at c, and the drone heads out at c. So if you're down at Earth watching this, what's the speed of that drone? What do you think the speed of that drone is? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, bless you. It is C. The answer is C. They don't add. They don't subtract. If we were on a train, like the spaceship, and we throw a baseball, sure, those two speeds would add. We're used to that. That's not how it works for light. It's an absolute, because it is not relative to anything else. So you can't add it to the speed of the spaceship. So think about that. You're on a spaceship. You're going the speed of light. You turn on a flashlight. Well, it goes at the speed of light, right? Are you traveling along with the light beam? If so, in that reference frame, you're at rest with respect to the light. You're not going to measure the speed of light to be 0. You're going to measure it to be c, speed of light. So you can't ride along with a light beam, as a lot of people have done a thought experiment. Wouldn't it be great to just travel on a light beam? You can't, because it's not relative to anything else. Yeah?
So what if something was moving slightly less than the speed of light?
Okay, slightly less than c.
And we're moving in an object, or maybe a train that's also slightly less than c.
Okay, so we're both moving slightly less than c?
Yeah, so in a normal scenario with the baseball, they would add up.
Yeah, if we're moving slightly less than c, and we toss a baseball out at 50 miles an hour, then back on Earth, watching this, we would say the speed of the baseball is not 50. It'd be the speed slightly less than c plus 50 miles an hour.
So what if
They do add.
What if that, slightly less than c plus 50 exceeds c? Does that make sense?
Yes. So what if the speed that we see the baseball going, we calculate it to be greater than the speed of light? Well, let's discuss that, shall we? We're going to get to that. You can put your clickers away. We'll call that good. Basically, I'll do that one first. Momentum is mv. That's what we learned. It's inertia in motion. Some people, and you might hear out there, that as you go faster and faster and faster and approach the speed of light, mass increases. That's not technically correct. Classically, that's what it appears to happen. But really, it's the momentum that increases. Relativistically, they throw in the Lorentz factor. Remember, it is, I'm going to put it over here. That was 1 over the square root of 1 minus the speed you're going, squared over the speed of light squared. That funky factor. Called the Lorentz factor. And before I finish this is kind of where we left off. If you're going the speed of light, follow this. This will be c squared, correct? So this ratio will be 1. 1 minus 1 is 0. The square root of 0 is 0. What's 1 divided by 0? Black hole. Infinity. Yeah, if that, you're going the speed of light, then the Lorentz factor is infinity. So as you approach the speed of light, this factor gets bigger and bigger and bigger and approaches infinity. Let's say your velocity is really slow, like what we're used to, me. Something really slow compared to the speed of light, which is zippy. This ratio is essentially what? 0. It's very close to 0. So 1 minus 0 is 1. Square root of 1 is 1. And 1 over 1 is 1. So if v is slow, then the Lorentz factor is 1. So can you see, the Lorentz factor is always going to be 1 or something greater. So if it's near 1, you're going really slow, what we're used to. And this factor doesn't really affect anything. See over here, if you're going slow, that just is a 1 and it's back to what we're used to. But if you're going super fast, then the Lorentz factor increases. And if you're going the speed of light, it says it'd be infinite. It would your momentum would be infinite. And there's no impulse you can apply to change some object's momentum an infinite amount. Remember impulse? That's a change in momentum. You're trying to change the momentum. You couldn't do that. So the faster and faster you go, the more energy it takes, the more momentum change in momentum is required, an impulse, and it just becomes impossible. According to special theory of relativity, it is impossible to ever get the speed of light. So any baseball that's just trying to go faster than the speed of light could never get there. Any object with mass cannot go the speed of light, which is one of the main reasons they say light is massless. It has no rest mass.
So would it just disintegrate?
Would it disintegrate?
Or to keep that ratio constant, would that mass have to go down? Or
Well, classically, that's how we kind of rationalize it. It seems like the faster and faster you go, it takes more and more energy. So it's like the thing has more and more resistance, right? Inertia, getting heavier, more mass. So people have said the faster you go, your mass increases. Sort of. Your inertia increases. Inertia of motion. Momentum approaches infinity also. And you know, something that's coming at you with more and more momentum, it's going to take too much to stop. Or getting it up to that speed. You can't just keep pushing on the thing. Let me give it a kick. Get it up to a higher speed. Now give it another push, and it gets higher, faster. Another kick, and faster, 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 and gaining more and more and more and more momentum. The point here is the faster it gets going, the harder it gets to change its momentum. Because it's approaching infinity, the change. You're trying to go from something up to infinity. And that requires a force, right? It's going to get harder and harder and harder, and you can't do it. You can't get all the way there because of that infinity. So, yeah, that's why a lot of scientists say the speed of light is a limit. You've probably heard that. It's a speed limit. Nothing can go faster than the speed of light. Let me qualify that. Nothing with inertia can go faster than the speed of light. Yeah. The speed of light is an impulse itself. It's a very wussy impulse. Because essentially they've defined light as massless. So if you throw nothing that way, you don't recoil. Yeah, they've tried to show this. Now, there's good experiments with that. They've tried making a very, 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 very good vacuum and shining light on something, high-powered lasers, to see if it can get something to move, because if it hits it. And I'm not sure if they've been successful. Usually there's heat involved. It heats something up and the particles recoil. But if you can get rid of all those particles, yeah, essentially the thing just sits there. I personally don't feel light is completely massless, but I have no bearing in that. Because that's in a realm, we don't know. We haven't been able to test it. But according to the theory of relativity, it's massless. So that wouldn't help us. Likewise with this, kinetic energy would have a Lorentz factor in it. So the faster and faster you go, what was that? You're going to have to throw that in there too. It's just going to take an infinite amount of energy to get up to the speed of light. So, can't happen. I would like to be able to try. And we're going to keep trying. So this time dilation and length contraction. Now, before I get there, the very last paragraph talks about the correspondence principle. Correspondence principle. Basically, it just says any new theory must agree with the old, if the old was correct. And so what that means here is these equations better match up with everything I've just taught you, Newton. And they do. That's the beauty of it. If you're going really, really slowly, what's the Lorentz factor approach? 1. And so this Lorentz factor doesn't change anything. This would be back to 1/2 mv squared. This will be back to mv. And at the very end of last class, we had the times varied by the Lorentz factor. The time it takes for the light to travel up and down versus across, that's how we came up with this. There's a factor. If that's 1, well, they're the same thing, and everybody's simultaneous. We're happy with what we're used to. But if you're going relativistic speeds, this gets bigger and bigger and bigger. And so one of these times takes longer than the other.
Could you go back to that equation? E equals half mc squared plus mc squared. What were you talking about in that case?
That was, like I was using the book as an example. Just sitting here like it's rest energy. Just because it's of its mass, there's associated energy with it. It's like latent energy. It took energy to form this, so if somehow this were to just disintegrate and all the molecules and things would rearrange, that would release some of that energy. And the book might not exist in this form anymore, so we wouldn't say it has mass. It doesn't seem to be matter in the book form. It would be matter in protons and neutrons and things. And that would release energy. That's this idea. That's this term. It has this much energy at rest. But if you get it moving, you add energy to it. And now it's kinetic energy also, because it's all moving together. So total energy is the energy of motion plus this latent energy that's stored in it. That's what I was trying to show there.
So latent energy isn't it a potential energy?
It's like a potential energy. They're related, just like this. The ball has gravitational potential energy relative to the floor. So it's like latent. It's not doing anything now, but it's stored in it somehow relative to the floor. And, oh, there it is. It's like we released it. What this formula also tells us, though, is here versus here. According to Einstein, this has more mass than down there, because there's more energy associated with this here. And energy and mass, more technically, so you get less confused as you think about this, energy and inertia are kind of like two sides of the same coin. It's almost as if they can convert one to another. Both are still conserved, it just changes forms. It's kind of like they're both a form of the same thing. And here, this has more potential energy than down there. So if energy and inertia are related by a factor of c squared, it's the same thing as saying it has more energy. It has more inertia, more mass. Can you see this is a negligible amount for us? But when it gets to subatomic particles and in quantum physics, they have to account for this. These particles seem to have more mass when they contain more energy. If they give up that energy and it goes somewhere else, they have less mass. Yep.
I can understand the Einstein point of view, how it gains mass when it's on the table as opposed to on the floor. But
Okay.
isn't that inconsistent with the other thing we learned about how in a system energy is conserved and overall energy?
And you're in very good company with high up there physicists. A lot of people say, well, doesn't that break conservation of energy? No. Total energy is always conserved. A lot of people think, oh, let's just take this lump of matter and disintegrate it, poof, and now it's in energy. Wait, we just created energy? Well, now the total's not the same, is it? We had so much to begin with, and now we have more? That would break the conservation of total energy. Don't think of it that way. That's not right. Think of it as its mass. It has inertia. And Einstein says, if it has mass and inertia, there's latent energy there. It's like congealed energy. They're one and the same thing. That energy's there already. We've just released it. So the total's the same. And if this disintegrates, it's not like we've disappeared matter, because it's in a different form now. So mass and energy are still conserved. This doesn't mean, a lot of people, the media have warped it a lot too. You can't just poof something and or all of a sudden out of pure energy, things come together and you've created matter. It appears that way to us classically. We've seen that where like two photons come together and all of a sudden there's an electron and a positron. Well, no, they're one and the same thing in the first place. It's just like they changed forms. That's what this equation really tells us. Mass and energy are like the same thing. Or think of it this way. Inertia is like a dipstick for measuring how much energy is there. You know, your dipstick for measuring the oil in your engine. You can pull it out and get a gauge for how much energy is there, how much oil you can use up. That's kind of how inertia, I like to think of it. It's like a dipstick to know how much latent energy was there in the first place.
Is that what they do for the Large Hadron Collider?
Yeah, the Large Hadron Collider has to account for relativistic because they're cruising near the speed of light. So all of these, they have to include the Lorentz factor and account for this. Because they're very, very small, so it's a comes into play more. Us macroscopically and big, we don't really notice it ever. However, this whole relativity stuff, you should be grateful for it. Satellites and your phones, the GPS, Global Positioning System, would totally not work if they did not account for the theory of relativity. Because the satellites are going fast relative to us. And they're approaching relativistic speeds. Some are. And so if they did not account for this, the times would be off. And if a time is off just by seconds, you can be off miles down here. I don't know how well you guys know how your GPS works. But you just move a little. Or one time it says you're at this height, and then later it says you're at another height. Well, it depends on how many satellites you're using. But they're in a moving reference frame, uniform moving reference frame, whizzing around. And so, yeah, time and space to them is a little different than it is for us. And if they did not account for relativity, we couldn't trust them. They'd be useless. So next time you're getting your location or tagging the picture you took where you're at, think about relativity. It'll remind you of this conversation. I find this interesting. Let me make a table real quick. This is good. This is good stuff. We'll finish. I can tell there's a couple things I won't get to, but we can do that at the beginning and next time when we review. The Lorentz factor. If it's a 2, how fast are you going? 87% the speed of light. So in order for it to seem the time difference of twice, you'd have to be going 87% the speed of light. So we're talking fast speeds here. That's why we don't notice any of this. Let's see. 3 is 94. 4. And this, I just plugged them into that equation and worked it out. What's 4? 97%. 5, 98. 7, 99. 10 times. 99 and a half. 22. 99.9% the speed of light, and you've changed things by a factor of 22. Let's jump up to my favorite, 99.99995% the speed of light. Now you've changed things by a factor of 1,000. What's this mean? This means, okay, I'm off on a spaceship cruising around at 99.99995% the speed of light. To me, nothing's different. I'm at rest with respect to my frame of reference, the spaceship. We're not moving relative to each other. So time is normal to me. Lengths are normal to me. I don't notice any difference. Life goes on. But you observing me in a frame of reference that's at rest relative to my speed, it looks like my time is slowed down to you. That everything that I observed takes 1,000 times longer for you. I mean, you think it takes 1,000 times longer for me. Nothing seems different to you guys. Your time's normal. My time's normal. Again, because you're at rest with respect to your frame of reference. I'm at rest with respect to my frame of reference. So normal, normal. But when we look at each other, I think your time is 1,000 times slower. Because you're in motion relative to me, aren't you? And I'm in motion relative to you. So my time seems to be 1,000 times slower. So if I were to throw a baseball, whoosh, for me, it would just seem normal. To you guys, it seemed like it would take 1,000 times longer to get where it was at. And if I watched you throw a baseball, it'd seem normal to you, but it would seem like it takes 1,000 times longer for me observing you. And again, we're both right. It just has this, because motion's relative. Now, if time's different, space is different. And that's the length contraction. It's pretty much just summed up by this. One length is the other length divided by the Lorentz factor. It has to be the inverse. If one's getting smaller, the other seems to. So the distance, just take a meter stick. Oh, I don't have one. The length of this book is, let's call it a foot. I get a foot. But if you're observing me cruising around at 99.99995% the speed of light, you will not measure this space to be the same length. You'll measure it as 1,000 times shorter. And vice versa. Because you look like you're in motion relative to me. But we're both right. The ratio stays the same. Speed of light stays the same. So we're not going to calculate lots of stuff, but I want you to know these two things. That time dilates, seems to stretch out for those in motion relative to you. Things are normal for them, things are normal for you, but if you try to measure their time, things get wacky. It slows down. And all time, even biological clocks, we would seem to age at different rates. So this is the twin trip. That there's a cheesy animation that the author made that'll help us. Read that in your book. It shows little light paths. But the gist is, if you two were same age, and you head off on a spaceship near the speed of light and head out for years and then come back, when you come back together, you will no longer be the same age. Because the one moving will age more slowly. That's time dilation. And while you're moving, lengths will look different. But when you get back in the same reference frame, you're both at rest with respect to each other. Now you'll tick off the rest of your life at the same rate. But one of you will be older than the other. Give that some thought until we meet again Friday. Take care.